Trigonometry, Chapter 4, Graphs of the Circular Functions, Section 1, Graphs of the Sine and Cosine Functions, Video 1, Periodic Functions. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous chapter, we learned about radian measure and the unit circle. We were introduced to the 6 circular functions defined on arcs of the unit circle, 6 functions that bore a striking resemblance to the 6 trigonometric functions we had seen twice previously. Once from the XYR perspective, and once from the right triangle perspective, commonly known as SOHCAHTOA. We also learned about the relationship between linear speed of a point on the edge of a spinning disk and the angular speed of that disk. In this chapter, we take a closer look at the nature of the 6 circular functions. We analyze their periodic nature and study their graphs. In this section, we construct the graphs of sine and cosine. In this video, we define what it means for a function to be periodic and see how this applies to circular functions. Previously, when evaluating trig functions like sine of 765 degrees, we reduced the input by finding a coterminal angle with 765 degrees. Since 765 degrees equals 45 degrees plus 2 times 360 degrees, we knew that sine of 765 degrees equals sine of 45 degrees, which equals square root of 2 over 2. I want to pause for a second and clarify how you figure out that 765 degrees is 45 degrees plus 2 times 360. Just subtract 360 until you can subtract no more without making it negative. 765 minus 360 is 405, and 405 minus 360 is 45. So we subtracted two 360s, and the difference was 45 degrees. But sine of 765 degrees equals sine of 45 degrees, both of which equals square root of 2 over 2. Now, when a function eventually repeats values, such as sine repeating values every 360 degrees, we call that function periodic. A periodic function is a function f of x that regularly repeats outputs. More rigorously and specifically, there exists a number p not equal to 0, such that f of x plus p is equal to f of x for all x in the domain of f of x. The least such positive value p is called the period of f of x, and the behavior of f of x over one period is called a cycle. Again, all this functional equation is saying is if I take a number and add a certain value to it, I'll always get the same outputs, no matter what the x is. Now, recall the definition of f of x equals sine of x as a circular function on the unit circle. If an arc of length x in standard position on the unit circle has a terminal point P, then sine of x is the second coordinate of P. Now, you may be wondering why I didn't put x and y here. Well, I deliberately avoid referring to the coordinates of P as x comma y. This is because doing so could initially lead to confusion, because we'd be using the x in 2 capacities. Right now, we are viewing sine as a function whose input is x and whose output is the second coordinate of the terminal point. In other words, we're trying to think of the length of this arc as x, so putting an x over here as the first coordinate of this point would be duplicitous. We'd be using the x in 2 capacities. Wish I had more light behind me. 1 second. That's a little bit better. All right, since f of x equals sine of x will repeat values once we make a revolution around the unit circle, it is clear that f of x equals sine of x is a periodic function, as are the other circular functions. But what is the period of f of x equals sine of x? Well, the value of f of x equals sine of x will clearly repeat after making one revolution around the unit circle. Since one revolution is 2 pi radians, the period of this function is 2 pi. Now, technically, we say it might be the period since we haven't verified that 2 pi is the least such value showing periodic behavior, but I'll leave it to you to verify that no smaller positive value works as the period. As such, we can say sine of x equals sine of x plus 2 pi for all x in the domain of sine. In other words, for all x in the real numbers. Using a similar argument, we can determine that cosine also has a period of 2 pi, namely because cosine is the first coordinate of this point, and making one revolution, aka 2 pi radians, takes us to the same point. As a consequence, cosine of x plus 2 pi equals cosine of x for all x in the domain of cosine. In other words, for all x in the real numbers. Since secant and cotangent are reciprocals of sine and cosine, it stands to reason that they have the same period, 2 pi. Thus, for all x in their domains, secant of x equals x plus 2 pi, secant of x plus 2 pi equals secant of x, and cosecant of x plus 2 pi equals cosecant of x. Now, you might speculate that tangent and cotangent also have period 2 pi, because one trip around the unit circle takes you back to where you started. Although it is true that both tangent of x plus 2 pi equals tangent of x and cotangent of x plus 2 pi equals cotangent of x for all x where the functions are defined, the periods of tangent and cotangent are not 2 pi. Why? Or why not? Because 2 pi is not the least such value. We will see later that the periods of tangent and cotangent are actually pi, not 2 pi. Now you try. Pause the video and try the following. Fill in the blanks. If a function has period p, then f of x plus p equals. For example, sine x and cosine x both have period blank. And although tangent x plus 2 pi equals tangent of x for all x where both functions are defined, the period of tangent is not 2 pi, but rather just. Pause the video, give it a try. All right, if you haven't paused the video, here's your warning. Here's your heads up. Spoiler alert, 3, 2, 1, and your solutions.